In this final video on our series of regular and context-free languages, we're going to be able to check language syntax by referring to BNF or syntax diagrams and formulate simple product rules. We're going to be able to explain why BNF can represent some languages that cannot be represented using regular expression. So first of all programs, as we know, must follow strict rules regarding their structure, and we call this syntax. So here's 3 for loops, but they're all being implemented in a slightly different way depending on the language. And as we know, syntax in a language is key and absolute. In order to translate source code into machine code, all the rules of a given language must be defined totally unambiguously. Spoken languages, such as English, are so imprecise we can't even use them for defining unambiguously the grammar or syntax of a computer language. Just an example, take a look at this phrase, "I saw a man on a hill with a telescope." So it's pretty obvious what that phrase means. You've probably conjured an image up in your mind. But to a computer program, it's not obvious. What does this phrase actually mean? I saw a man on a hill with a telescope. There's a man on a hill and I'm watching him with my telescope. Now that may be the image you conjured up in your head, but what about this one? There's a man on a hill who I'm seeing and he has a telescope. I saw a man on a hill with a telescope. What about there's a man, he's on a hill, which also has a telescope. I saw a man on a hill with a telescope. How about I'm on a hill and I saw a man using a telescope. I saw a man on a hill with a telescope. And if we take this a stretch too far, how about there's a man on a hill and I'm sawing him with a telescope? Now this may be a bit ridiculous, but the bottom line here is that our language is totally inadequate for defining the syntax of a computer language. This is where we defer to BNF, and it's known as backus-naur's form, named after 2 people that invented it. It's a formal mathematical way of defining syntax unambiguously. It consists of a set of terminal symbols, a set of non-terminal symbols, and a set of production rules. Now, we already know that regular expressions can be used to help us describe a simple language by specifying patterns of strings which match conditions. Many aspects of languages can indeed be defined using regular expressions, but it's both lengthy and time-consuming. Some aspects of languages, such as the use of nested brackets, can't be defined using regular expressions at all, and this is where we turn to meta-languages. Backus-naur's form is an example of such a meta-language. Okay, so let's get into BNF and let's look at how it's defined and how it will look in the exam. So BNF statements come in this form. There's the left-hand side, and the left-hand side of the statement is always a non-terminal symbol. There's then this notation, which means is defined by, and then there's the right-hand side, and the right-hand side is a sequence of symbols, terminals or non-terminal. So whenever you see a BNF statement, it's this section is defined by this section. Let's start with some simple examples then. So we're saying a digit is defined as, now the vertical line means or, so this means a digit in this particular language is defined as either a 0 or a 1 or a 2 or a 3 up to a 0. Let's have a look at another example. In this particular language, a letter can be defined as an A or a B all the way up to Z. We could take that one step further, and having defined a letter, we could say a word in this language is defined as letter. So this means a word is a letter followed by a letter, and by this definition we can see that this wouldn't be a word and this wouldn't be a word. but these ones would. Don't forget, it has to be 100% exact. We know that a and she is indeed a word, but in this language, a word has to be a letter, and a letter has to be one of A through Z. Now, in the last example, a word had to be 2 letters. So we could extend our definition to say a word is defined as a letter or a letter. So now in this example, this is defined as a word, these two are, but still this one isn't. Now we could obviously continue and say a word is defined as a letter or a letter, or a letter, but something doesn't seem very right about this. So let's move on to the next slide. Now, clearly the definition of a word could get ridiculous if we had to define how many letters. This is where BNF allows us to use recursion. So let's just have a look at this. We can say a letter is defined as one of these symbols. A word is now defined as a letter or a letter word. And that recursively calls itself because a word is a letter or a letter word. In this way, we're defining a statement in terms of itself. So this now means a word is a single letter or a letter in a word. Or to put it another way, a word can now be any number of letters. This process of working out if any given statement is valid according to the BNF production rules is called parsing. We can build these production rules up to as much as we like to make higher level statements. So you can see here I have letter is any of these symbols, a word is a letter or a letter word, a space is a space, a full stop is a full stop. And then I've used all of these production rules to create a sentence. And in my circumstance, a sentence is a word and a full stop, or it's a word and a space and then recursively calling sentence again. Now, syntax diagrams are simply a graphical representation of BNF. The two methods of representing syntax map directly onto each other. Any BNF textual statement you can draw as a syntax diagram and vice versa, and you may be expected to do both in the exam. It uses the following symbols. This is a terminal element, so it can't be broken down any further. This is a non-terminal element, which is defined by another syntax diagram. And this shows how we can use a terminal element more than once. So, here for example, we've defined a digit as either a 0 or a 1 or a 2, and you can see there we travel through the diagram once, and we can say a number is any sequence of digits together. Looking at a slightly more complex example, here's our BNF for earlier, and we're saying we want a sentence. So here we have a letter is defined as any single letter. There's our space, there's our full stop, and a word consists of any number of letters. And here we have the syntax diagram for a sentence. So a sentence equals either a word or a full stop, or a word and a space, a word and a space, a word and a space, and eventually a word and a full stop.